Okay, question 54. Rank the following compounds in order of decreasing acidity. So when we say decreasing acidity, keep in mind what we're saying is increasing pKa. So the higher that pKa number is, um, the less acidic the compound is going to be. Okay, so the obvious comparison point for these three molecules should be this middle carbon. So thinking about this middle carbon right here. So we've got those two hydrogens coming off. Okay. Um, if you look at this rightmost molecule, it should be obvious that you got two pi bonds here versus one pi bond here and zero pi bonds here. Now, obviously, the hydrogens that are attached to the sp2 carbon are going to be a bit more acidic than the hydrogens attached to the sp3, but in this case, there's not really going to be a chance to delocalize electrons very well for either of these situations. And we don't have, a pi bond here to deprotonate. So if we tried to deprotonate the sp2 carbon, it would be an apples to oranges comparison. So that's why we're not going to do that. So we're going to ignore the hydrogen attached to the sp2 and talk about the hydrogens that are attached to the sp3. Okay, so let's go ahead and just focus on one of these hydrogens and deprotonate all of these guys. So we'll deprotonate, 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 and I'm not going to show the mechanism. I'll just say minus H plus for all three of these, and show the resulting conjugate base. So let's go ahead and copy paste everything. Go ahead and copy paste and put it down below. And what I'll do is just erase one of the hydrogens for all these guys. I'll just go ahead and erase them both. And you don't really need to show that second hydrogen. It's just kind of, again, implicit that it's there. So go ahead and draw the result. If we lost one of the hydrogens, we'll have that negative charge on each one of these guys. And so once we have a negative charge, we can begin to try to delocalize that negative charge. So for this molecule on the left, we can try to delocalize in this way. We can draw electrons going up, and if we make a bond, we have to break a bond. So we're going to have to break that bond, draw a resonance arrow, and if we do that, we'll have this cool looking guy, and the negative charge is going to be on the right. Okay, so we have one resonance form for the deprotonated conjugate base on the left. For this guy, there are no resonance forms. There are no pi bonds to delocalize onto. Everything else is sp3 hybridized. So that negative charge is not moving from where it's at. It's stuck. Okay, so there, in this case, are going to be no resonance forms. So no res forms. Okay, and then if we go to the one on the right, we can either go to the right, push that negative charge to the right, and do basically the same thing as we did with the molecule on the left. Okay, so we can do that. Push the electrons to the right, and we'll have a negative charge on the right. Or we can do something a little bit different. So that's one possibility. We can go to the right, or we can go to the left. And because both are possible, both will indeed happen. Okay, so we could potentially go from the pink to the blue, but only if we drew another set of arrows. So if you drew another set of arrows, you could potentially draw them like this, where we drew these electrons going this way. And it looks like I forgot to add a double bond up above. So always count your double bonds. It's something really easy to mess up. I even just messed that up. So double bond here, double bond here. So we should have two in the top as well as the bottom. And so we do actually have this second double bond right here. Okay, because we didn't actually show it moving in the original molecule. So you can get the same molecule for the pink or the blue from the pink or the pink from the blue, but you have to show a different set of electrons or arrow pushes for the electron movement. Okay, so anyway, that was kind of a tangent, but going over here, if you compare and contrast how many resonance forms you have, these two are the same on the right, so these two are the same. So we really have 1, 2, 3 res forms for the one on the right, 3 res forms, and we have 2 forms on the left. So 0, 2, and 3 res forms. Okay, so I guess technically you could technically call this a res form, but there is no conjugate to it, so calling it a resonance form is kind of a misnomer. But anyway, I'm really going on tangents for this one. But okay, anyway, so decreasing acidity. The compound that's going to be the most acidic, again, is going to be the compound that is the most stable as its conjugate base. And the most stable conjugate base is going to be the one that has the negative charge that's most dispersed. Okay, so of the three, let's go ahead and label these guys. So have A, B, and C. Compound C is going to be the most stable as its conjugate base, and so this is going to be the most acidic. Compound C, before you lose a proton, this is going to be the most acidic as 1, so this is going to be 1, and least acidic is going to be 3, so this is going to be 3, and this is going to be 2. Okay, because comparing A to B, the conjugate base for B has 0 resonance forms, really unstable negative charge, versus A. A has a way to disperse that electron density. It's going to be a bit more stable. Okay, so C is the most acidic, A is the next acidic, and C is the least acidic. Okay, and again, all going back to stability of the conjugate acid, or the conjugate base, and the conjugate base is going to be the most stable if it has a lot of resonance forms. Okay, all right, next question.